And I have this really, really nice equation. D squared theta dt squared is equal to minus G over L. And then I get to this last part and I see that there is a sine of theta there. And I have an unhappy face because what I would really like to be there is theta, not sine of theta. If I flash us back to our equation for oscillatory motion, right? We want a second derivative equals a negative constant times the position function, right? And here, theta is serving as our position function, but we have sine of theta instead of just theta. So you might look at this at first glance and say, oh no, I'm in trouble. In particular, sine is not a linear function of theta. So this is actually a really, really challenging differential equation to solve. We might be totally out of luck at this point. But before I give up altogether, I'm going to see what I can do with the sine function. So I've gone ahead and graphed sine of theta here for us. Theta is the one that starts at 0. It's an oscillatory function, and then it pops around and hits 0 again at theta equals pi. Now I only have to worry about this function in between 0 and pi over 2 because that's all I can really do with a pendulum. If I try to go higher, the string doesn't do what I want it to do. But even so, this function is definitely not equal to the theta function. It's not quite a straight line, which I've graphed here. The orange graph that you see is the function theta, which is just a straight linear line that starts at 0. But there is something interesting which is going on here, which is that if I zoom in on this picture and I look at just the angles where theta is kind of small, maybe in the half a radian or even less than that, then actually this doesn't look like it's that different. Sine of theta and theta are pretty close to each other. And that's a fact about the sine function that is called the small angle approximation.